Organizer.
So we are on it. Are you ready to go?
I'm ready.
Okay, so we got two talks in this hot session. I had so many hot talks. I don't know why we have a hot session particularly. It's just yeah. Anyway, so Martin Hoffman will talk after Ulrik in about an hour's time. First, Ulrik is going to talk. What do you need to know about his talk? Well, all you need to know is got the word nominal in it.
Yeah. Thank you, Andy. Yeah, so this is, I got the email from Andy requesting volunteers for talks for this hot seminar on June 20, and I had just come up with this idea maybe 10 days before, and I thought, that'll be great. I'll just, we welcome work in progress, so this is very much work in progress. So it's not a fully baked thing yet, but you can follow along on, I put out something up on GitHub. I'm sure if you go to my GitHub profile, you'll find the repository, and there's a little bit of active formalization. I'll tell you about it in a little bit. So, what is this about? What is the motivation for this experiment? And very much is an experiment. Well, so together with Flores and Egbert, I've been thinking about group theory in HOT, in particular about some higher groups, but this happens to be about an ordinary one group, namely the finitary symmetric group, which is the subgroup of the automorphism group of natural numbers, which only move finite, or those permutations that only move a finite subset. Okay, and so we can represent this in HOT. I'll tell you how in a little bit. What this is useful for is, well, one thing it's useful for is that the sets with an action of this group are known as perm infinity of perm n sets, and a certain subclass of those, namely with those with finite supports, are one model of nominal sets. So we get one model of nominal sets is finitely supported infinity sets. So I thought maybe it would be fun to see, since we have this gadget and very easy to reason about it reason about it in HOT. See how much nominal theory we could do in HOT when we have this gadget. Of course, if you just want to do the set theory, you could use any of the other models of nominal sets, and you would actually get I'll tell you what the other models. So other models include, let's say, the continuous infinity sets. You can take the continuous of n sets, and there I have to tell you that we then put a topology on these groups, which I'm actually going to ignore for this talk, but the subsets of bare space, they have a natural topology. Some other models are the sheaves on this category of finite sets and monomorphisms off with the atomic topology. If you know what that is, that's fine, otherwise it doesn't matter for this talk.
So what do you mean by model?
A presentation of the topos. So the nominal sets form a topos or a category. If you don't care about the topos structure, form a category, and there are very many different equivalent presentations of this category.
Yeah, okay.
That's what I mean. Or you can make presentation for model here. Yeah, and this turns out to be also the classifying topos of infinite decidable objects, and there are many more. And so, for instance, doesn't really matter. So the thought was, well, this is all fine and good. These are one toposes, and HOT is about infinity toposes. So what would be the correct infinity topos of nominal infinity groupoids? And I'm not going to reveal that today. This is still just sort of exploration. but it's maybe something to think about. Anyway, the motivation is to perhaps make life easier when reasoning about syntax with binding. Syntax with binding. So in when we do ordinary mathematics in type theory, there's something called setoid hell, which you run into if you don't have hot, which is you have to do quotients, so you add an ad hoc equality relation on your types, and then you end up with these setoids, and everything has to also take care of the setoid, and you're at setoid hell. And when you do reasoning about syntax with binding, you end up in what Elias called the weakening hell, whereas you always have to insert these weakenings everywhere and carry them around, and they're just sort of when you just reason with things about names, you never think about weakening. It's just something that's invisible. So if hot can help us escape the setoid hell, perhaps it could also help us escape the weakening hell. This is what I want to explore. Okay. So I still haven't said what's really, hot. So okay, so there's this thing about we have as a one topos, we could reason about this in hot in all the standard ways. We could formalize each of these things, particularly maybe this sheaf model, but we wouldn't have access to any of the higher topos, higher toposes that restrict to the topos of nominal sets. Is there a question? So when we do have that, when we go instead of to the nominal sets, we just go look at the sigma infinity sets, because the sigma infinity sets, they're just maps from B sigma infinity to the type of sets. And that's something that's very easy to reason about. You don't have to do any translation to work with this inside type theory. You just work in the context of a variable of this type. Okay, so that is one motivation for me. Perhaps this is, from a practical point of view, is something that's worth doing. Yeah.
Did you already explain what this means?
No, I'll do that in this time. I'm still at the motivation stage. I'll explain the terms. Okay. So, the next thing I was going to say, where you could take B sigma infinity to be a K sigma infinity where
K.
That's one thing. But actually, I'm going to tell you a different model. So you don't even have to know what this is. This is for the people, the subset of the room who knows what this is. Actually, there are many different presentations of this, and for practical purposes, which particular instantiation you take might matter.
I mean, all I know is K is for Kelly, but I don't know what it is, right?
It's actually not for. There's nothing to do with K. It's an Eilenberg-MacLane space.
Well, I thought Kelly was in there, but
So there's some type which is connected and one truncated, and this loop space is this group. Okay.
Are you in type theory now or not yet? Do you intend this in that kind of synthetic sense?
Yeah.
Being in type theory now or not really?
Yeah. I intend to do everything except when I come back to this question about infinity topos at the very end.
Right.
Maybe that has something to do with it.
But this board is in type theory. The previous board is the Shanuel topos.
That's just ordinary mathematics, not formal in any sense.
Yep, okay.
Where set is H set.
Inside. This would be H set.
So somehow on the left-hand side you've got a type with extra structure and
There's a groupoid here, and this
Yeah.
is a groupoid. These are equivalent groupoids. But okay, so maybe I was having a point. We can also look at this type of maps into type, and this would then be an infinity topos, which when we look at the zero truncated objects in there, you get this. But this is not the Shanuel topos. This is some sort of larger object. But you can still do nominal stuff in there. And I want to perhaps think about, well, what kind of nominal type theory can we do in the context of this type?
So is this supposed to capture Andy's nominal acta?
Nominal?
Acta?
There will be some, you can interpret some type theory in here. Okay, maybe I was going to mention this later. So the idea is this type you can define without any other axioms. So once you have hot with a minimum of computational resources like a univariate universe, that's actually all you need for one description. If you have a homotopy push-up, you can give other descriptions. And then you don't need any axioms at all. You can just work nominally by working in this context. Whereas if you had another nominal type theory, that would be some other axioms and computation rules you would impose, and you could hope that it could be interpreted in this type theory without axioms. And that is some wished for hot type theory that computes. So computational type theory, like they do in at CMU, or cubical type theory. Actually, for things I want to do, I want to use inductive families to make elements here, and I'll get to that.
Since we're interrupting you, can I interrupt you? So I have played around with sort of constructed nominal sets a bit a couple of years ago, and that was sort of predicated on representing the permutation group by through transpositions.
Yeah.
So you end up with instead of having a G set for the group of permutations, you just have a thing from names cross the thing to thing, which is just a swapping action. And there are a few simple algebraic equations that are just exactly enough to be equivalent to having a permutation.
That's right. Yeah.
So could one could proceed on the left-hand side with that sort of thing, but you'd still want to somehow do a hit kind of thing.
You could prove. Actually, let me. I was going to give a little table, contents of this talk, and I'll get back to the sigma infinity, this group, and this B sigma infinity is a ways of presenting it after a little detour. So first we'll do a little detour through group theory and hot in general. And then that's one thing, and then maybe what's so great about slice topos anyway. What's so great about slice topos?
Easy to eat.
Yes, particularly if the slices are very small.
Yes.
Okay, so this is the thing about group theory and hot. So groups and hot. And I'm just going to do this in a little table. So maybe one of the things you learn when you learn about hot is that you can think about a type as an infinity groupoid. That's at least also one of the models we have formally. So what does that mean? That means that if you look at a pointed connected type, well, that's the same as looking at an infinity group. And how does that work? Well, if you have this pointed connected type, that corresponds to its loop group. So the carrier of which is the identity type. And if you have two loops at the point, you can compose them and you can take the inverse and you get a nice group. Okay. And if there's no truncation level imposed on A, this is a higher group that's higher dimensional structure on the carrier type. Okay. In the other direction, if you say you think of some group G, we write BG for the pointed connected type, and we call that the de-looping of G. Because it's supposed to be a pointed connected type, such as the loops form recover G. Okay. Now, if we impose the truncation level, pointed connected one type, then we can actually, we can prove formally, because now we can define both sides inside type theory. the other things, we can just look at those things here. But if you look at point connected one types, then they're just ordinary one groups. The kind of things you learn about first year in an algebra course, right? And in this case, BG is also known as an algebraic plane space, but you can also recover it, for instance, as a type of G torsors. Again, if you don't know what a torsor is, it don't matter, but this is mainly to say that even in unimath, where you don't assume you have homotopy pushouts, you can still form this type of G torsors when you have a group. And thus you can form the type of, you can form the D-looping. Okay, you can continue this table for a long time. Let me just say that I've pointed in a map. It's the same as a homomorphism. And if you forget the pointedness of the map, you get a conjugacy class of a homomorphism. Okay, so that's all exciting stuff. And I'm going to leave it at that. It should get you through today, and I'll refer, there'll be some upcoming work followed. Flores and Egbert are writing something about this story. Yes?
So you said that you forgot, if you forget about a pointer, you get what?
You get a conjugacy class of a homomorphism. So you have some homomorphism, but it's not, you don't know where it is in its conjugacy class. Okay? But once you add the extra data of the pointedness of the map, that pins down an actual homomorphism. I'll give you an example in just a moment. An action is the same as a map from BG into some type of objects you're acting on. So an object of U with a G action is the same as a map from BG into U. Because this tells you, well, there'll be a point, and that tells you the object that's being acted on, and then the functoriality on the identity type tells you what the action of the loops are. Okay. We can also say, what is an automorphism group?
So that's an arbitrary type of action, not a usual set action. A type of.
Yeah, a type of action. So U is any type here.
Yeah.
And
Oh, I see.
yeah, if U is the universe, then it would be a type with an action. But if U is the universe of sets, then it would be a set with an action. And if U is some other kind of gadget, it would be that kind of gadget with an action. So the automorphism group of U in U is de-looped by, you get B U, and this is, you can just describe this as the image of the map from the unit type into U. So U is an object of U, and the identity type U equals U is the automorphisms. So all the things that are, so the subtype spanned by this element is the de-looping of the automorphism. Further, okay, so let me just mention a couple of other things. If we have an action on a type action, that is then a map from BG type, call it X. Then this has invariance, which we write, which a homotopy theorist would write like this: the homotopy invariance of X, and for us it's simply a pi type, which I'm going to introduce a little notation here. B. Another way, this is, to think of this as being the fixed points. At least, so think about if X is a set, happens to be one truncated, then this would be the fixed points of the action. And we also have co-invariance, and that's be the sigma type. Which is a kind of quotient that remembers how things are identified, and then if you take the set truncation of that, then you get the actual usual set quotients. Okay. And so one fun thing to remark is that the type of finite sets is the disjoint union sigma type, if you like, or the natural numbers of the B type. And I'm sorry, Chris, I'm going to use bracket n not for the linear order with n plus 1 elements in n maps, but of this type with n elements and no extra structure. This is the standard n elements set. Okay. I should say that here I mean, the finite sets are the Bishop finite sets, the ones that are merely isomorphic to some particular specified set of n elements, not other constructivist notions like Kuratowski finite sets. Okay, let me clear the board. When it's a hot day and you have this lamp on and you do hot, it's extra hot. That's what I wanted to say about that. Now, what's so great about slice toposes? Except that they're easy to eat.
Sorry, Ulrik, what was the H? What's the H in the previous formula?
That's the homotopy. It's for homotopy. It's because that's the homotopy theorist convention. And if you don't know the homotopy theorist convention, it's just a pi type and a sigma type. Okay, now think about any type you like. I'm going to call it I for the index. And then, of course, we can do all the judgments of type theory in this context of an I and I. And then you have all your favorite judgments. And everything works. You can do all the rules of type theory are invariant under extending the context by something. So you can just do type theory as usual in this way. And that's why it's so great if you can present your theory as just working in an extended context. But also there's something else that's nice, and is that if you have a map between the indexing types, if you have any f from I to j, you automatically get a system of adjunctions that you can work with internally. So let me write type to the I for the function space from I to type. And of course, I'm leaving out all the universe variables. There's the universe variables. Okay, type to the j. So first you get the map going that way, given by composition with f, since f upper star of some y at an index I is simply y at f of I. But then you get the two adjoints, and you can define them internally. Say the left adjoint is f shriek, and the right adjoint f lower star. So f shriek of an x. Oh, I need a little more space. Put it over on the left board. Okay, so f lower shriek of family x at an index j, well, this is going to be a big sigma type. So you pick an I, you give a path, f of I equals j, and then you give an element x of I. And that's it. And for the right adjoint, you just switch the sigmas for pi's, and you get that. So for every I, and for every way that f of I equals j, you get an element x of I. So it's a fun little easy exercise to see that we can prove at least the lower parts of the function parts of this adjunction inside. So for instance, so as a special case, if you take the projection to the unit type, you recover these invariants and covariants I was talking about before. Okay, and that's enough of a brief tutorial in group theory and indexed hot. So now I'll talk about this sigma infinity group. So I mentioned in the intro that there are many ways to define a de-looping of this. Now I'll just have to use. Okay. So there are many ways to define this. You could define it as the type, so B sigma infinity. Some de-looping could be the type of sigma infinity forcers. That's one way. You could do a hit where you say you have a point in sigma infinity, and then take your favorite set of generators. It could be the transpositions, or I suppose the adjacent transpositions, or all the finite permutations. So generators as paths plus relations plus the one truncation. So that would be, if you have some way of building hits in your theory, you can directly build this, maybe picking a very nice presentation. Okay. But it's also equal to the co-limit of the classifying types of the usual finite symmetric groups, where you extend, you have the map from sigma n to sigma n plus 1 that includes on the first n elements. And in fact, since we're doing things equivariantly, we don't even need this the homomorphism itself, because on a map of classifying types, remember, the map, just given a map from B sigma n to B sigma n plus 1, this gives you a conjugacy class of a map. When I don't tell you the pointedness, it's just the conjugacy class of the inclusion of sigma n into sigma n plus 1. So that's uniquely determined by, so I'm going to explore the model where we take as a de-looping of sigma n the B out of the canonical type with n elements. And if you had a different, say if you take as a model of B sigma n the hit generated by the transpositions or just thing, you get a map from here to here. You get maps, say from K sigma n1 to B out. And by B out n, I'm going to mean this image that I mentioned before. So it's all the sets in type, oh, it doesn't matter. Every type that is merely equal or the same thing, merely equivalent to this n element guy. And then of course it's a set with decidable equality because it transfers from this type to that type. Yeah, so you get a map from here to here just by the induction principle for KGN, but it's not so easy to say what the map in the other direction is, right? We get that this is an equivalence basically by the Whitehead principle. We know that this is truncated and has the right homotopy groups, so it must be an equivalence. But if you try to write down this map, it wasn't so easy to read in any case. So there's some intentionality matters. How you present these objects really matter for practical purposes. And I'm going to explore a little bit now what happens when we take this as our definition. And then we're going to take this co-limit, and the co-limit will then be along this sequence. 0, 1. So we co-limit, and typical object here is a finite set, right? And we can recover the cardinality of the finite set, of course. And then in this here, it maps to the type with one more element, and I'm going to write the new element on the right. And for reasons that will become clear in a little bit, it matters that I write it on the right. Okay. So we can also think of this perhaps a little more as a hit, the same presentation intentionally as its co-limit, where I have an inclusion map from the finite sets into B sigma infinity. And then I have a glue that tells me, so for any finite set A, IA is equal to I A plus 1. Okay, so that's another presentation of B sigma infinity, and That's what that's directly equivalent to this co-limit presentation, but it's very convenient to work with. All right, and what is nominal theory without atoms? We need atoms. So this should be a nominal type, in fact, should be a nominal set. So it should be a map from B sigma infinity to set, or H set if you want. And what it should be the natural numbers, or some other thing that's equivalent to the natural numbers, with the action given by these symmetric groups, this permutation axiom. So how can we implement that? Well, with this presentation, I can say that the atoms of IA are simply A plus the natural numbers. If you like, you can think of this copy of the natural numbers as being the, let's see, the k's in N, such that k is larger than or equal to the cardinality of A. Okay. I'm going to make a little picture. So we have a finite set of some cardinality that is A, and it has cardinal N, say N, no, yeah, N is the cardinality of A. And then I have all the rest of the natural numbers, which are not going to be moved by this permutation axiom. But now if I have, say, a permutation between, or an equivalence between finite sets of cardinality n, I can use that to swap this A for some other thing, and that implements this permutation axiom. And then the glue thing says that I can always, once I've activated these A elements, I can just activate the next element by adding one here. And that tells me how I should map A with a glue path. Glue A, well, what should it be? It should be a path from A plus n to A plus 1 plus n. So I need to come up with a path like that. But that's pretty easy because I can say this is A plus 1 plus n using canonical decomposition of n as the first element plus the rest. And then it's just associativity. Okay. But you now see that the other version of weakening or adding an extra element, if I add it to the beginning, that's no, so oh wait, let me step back. So I had this map of the finite sets, add a new element to the right. I explicitly said that in this model of B sigma infinity, this becomes homotopic to the identity. I also have another map, add a new element on the left, but with this notion of gluing the things together, that no longer becomes isomorphic to the, or homotopic to the identity. So
one of those weakening and the other was shifting.
yes, I'm going to call the thing that adds a new element to the right weakening, and I'm going to call the thing that adds a new element to the left shifting, because I made weakening into an equivalence. Okay.
The level. Yeah, the ground level.
Okay. So actually we can do more than shift by just one. We can actually get a whole map. I'm going to write it plus, I don't know if that's a good idea. This pulls from fin set times B sigma infinity to B sigma infinity, and allows me to shift by an arbitrary finite set. And what it does, of course, so you have your set A, and on a point constructor here, the finite set B, this include A plus B, and then I'll let you write down what it does on the glue, but it does the natural thing because I write things in the right order, and if I change the B by one on the right, nothing goes wrong. So this is like taking my stuff here, B is activated, and then I shift it over here. And now I have this sort of inactive blob A, which is not going to be commuted anymore. Next. Alright, so now let's look at what are the nominal concepts. Nominal concepts that we can talk about in this section. In fact, in the repository I experiment with indexing over all kinds of things, and also people have been indexing over all kinds of things. So indexing over just the natural numbers is kind of De Bruijn style thing. Then we have this map that, given a natural number, tells me a finite set of that cardinality. And you can also do the nominal theory by indexing over the type of finite sets. That gives you a renaming for free, but it doesn't give you weakening for free. And then, of course, we can do this thing, C sigma infinity, where now weakening is an equivalence. Some people also think, okay, let's just do all sets as our indexing set. That's not really compatible with this here. And I should also mention that there's, of course, a map from B sigma infinity into B n. And it might be interesting to see what happens if you take this as the indexing type. I would take you a little further away without any continuity principles from nominal sets, but it's still something that could be explored. So, okay, so in each case, a nominal set would be a map from the indexing type into H sets. A nominal type would be a map into the types. The elements would be the type that's being acted on, so the thing you have at the base point. And if you have the action by a group element is implemented via the identity type. So maybe some things that are particular to this thing here. We can use this shift map to talk about abstracting over a finite set of variables. So I have a finite set A, and I have a nominal type. I can form this nominal type by re-indexing along the shifting by A. So this is the thing that A x at B is equal to x at A plus B. Okay. And I should give a fair warning that there's also an operation in nominal set theory called abstracting the atoms. And that is sometimes, but I haven't checked, I don't think it's in fact always true, that it's the same as abstracting the one element set. But it is true if x is already a nominal set. So if for x with finite support. So in that case, at least it recovers the other notion. In fact, let me prove. Yeah, we can define what it means to have finite support. I think I'm going to lower. Oh, maybe I'll do that. So, yeah, so finite support should be an equivariant proposition. So it should be a map that for any B, B sigma infinity, so fix a nominal set. I want to tell you what it means for that to have finite support. I need to give an equivariant proposition on X. So and this is H. Okay? But in fact, since this type is a family of sets over this connected type, it suffices to tell you the meaning at the base point. So let me take that to be the inclusion of the empty set where I haven't activated any variables yet. So this means that there exists some n such that for any pi in sigma infinity, now I have a thing already at the initial state where I haven't activated any variables, and I can then take this shift by n out. I can shift this permutation pi out by n, act on it, act on x, and see whether I get x back. So there merely exists some n such that when I take any permutation that's the identity and the first n elements, and it fixes x. So this is now this proposition, and it then lifts to an equivariant proposition. And thus we do get the nominal sets in there as the things that have finite support, and one could prove, I haven't done so yet, but I think one could prove that one gets something that's equivalent to the other presentations of nominal sets. Okay, what's one of the fun things is we can do the closed terms, for instance. Because that's just the fixed points of the action. Right, so the closed terms of x are just elements of this pi type for every p give me an element of x to b. But more than that, I can also say, give me the terms of my nominal set or nominal type with free variables among this arbitrary finite set A. I don't know what is the notation for this. If I have a finite set, and I want then the terms with free variables in that finite set. I don't know what that is.
I haven't got a notation for that.
I'm just going
I've
to
got a notation for the things which avoid a finite set.
Yeah. Usually one would maybe talk about the function from nominal sets into, say, this sheaf topos, and then it would be the value at the sheaf topos at an index.
A of x or something.
But now it's just the fixed points of the shifted x. So give me an element of x. And in the other models, it would be hard to give this thing for an arbitrary finite set. You could do it for the canonical n-element set, but then you'd have to do some work to transport it to an arbitrary finite set. But in this model, you directly get that, which I think is kind of neat. Okay, then one would have to talk about the freshness relation. And what I'm maybe pushing a little bit under the rug is, in nominal sets, one has a very nice notion, sort of a uniform notion of name abstraction and name application. That I haven't developed yet. One can do it for, say, the atoms, and for discrete things, and for things that are built up of atoms and discrete things by positive operators, but I don't have like a uniform description of the name abstraction. That's something you want yet to do.
You'd expect it to be another hit, actually.
Yeah, maybe.
Because
It's a
in ordinary
kind
set
of
theory, it's a
quotient.
quotient kind
Yeah,
of thing.
yeah.
But of a very special form. But,
Yeah.
Nevertheless.
Yeah, maybe I should stop soon, but I want to say a bit more. I want to say it's quite easy to prove one of the fun propositions of nominal theory, that is that if you abstract by one of the atoms, you get equivariantly something that is the terminal object plus the atoms. And I'm just going to do it on a point constructor. So this thing, the left-hand side on a point constructor of say, IB, that is the atoms at 1 plus IB, which is 1 plus P plus N. But this is exactly 1 plus the atoms at IB. And it works out as well on the blue paths. It's quite easy to prove this proposition. Now for the, we have some experts in the room on continuity principles in constructive settings. So I want to come back to this thing that the nominal sets are the continuous sigma infinity sets. And, well, if you have something that's definable in type theory, we expect it to be continuous with respect to any natural topology you put on this gadget. So shouldn't it be the case that whatever I write down should actually be, that is a set with a sigma infinity action should be a nominal set if I just can write it down. But there are two caveats for that. First of all, you need x to be, if you want, so x, if x is a nominal set, or a sigma infinity set, when is this, so the continuous objects are the ones that have, another way of saying continuity is you're guaranteed to have finite support. And if you define this in type theory, we expect things should be continuous. So for e.g., so there's this continuity principle for functions on bare space. So for every f from n to the n into n, and for every point, it's a pointwise continuity, for every point alpha, there exists a natural number such that for any beta, if alpha's restriction to n is the same as beta's restriction to n, then f gives the same value, right? So that's a continuity principle we expect to be consistent with type theory, at least if we take the existence to be mere existence and not a sigma type. Is there likewise what consistency of the principle that if x is discrete, so if x has decidable equality, is it consistent to assume x has finite support? And it doesn't follow exactly from the continuity principle for bare space, because there I have to have something that is defined in all of bare space, a function. But here I have something that's only defined on a subset of bare space, so it's not immediately clear, maybe it is to the experts, that one can use one to conclude the other, but I don't see exactly how it should work. Maybe there's some continuity principle that encompasses both of these. Okay, that was this question about continuity. Oh, why do we need to assume x has decidable equality? Well, that's one way to say that I want x to be discrete. Otherwise, of course, you could do something like the decidable sets of atoms. This is a nominal set, and you have a point here, say the even atoms, but this doesn't have finite support. But that's of course because the natural topology on the set that's being acted on here is the Cantor space, so it's not a discrete set. So I only expect this to hold for things that are discrete, say in terms of having decidable equality.
So are the things that have finite support that retract of the bare space, or not?
No.
Okay.
No. Okay, let me finish. Any talk on nominal stuff should have an example about the untyped or unityped vector calculus. So let's just mention a bit.
Not if you're in Warsaw.
Huh?
Not if you're in Warsaw.
Not if you're in Warsaw.
And it has to be an example of an infinite state automata.
Okay. So putting in unitype for Favonius, let's say, unitype vector calculus. Okay, so if you have an indexing type with a shift function, you can define a family I into type with constructors as an inductive family. So it's not an inductive type, but it's an inductive family. And so you should have, what are the ingredients? You should have an indexing type. You should have some shift by one, say from I to I. And you should have a type of atoms on I. Okay? Then the constructors will be variables. So for every being a covariant function from a of I into lambda of I, we should have an application constructor. So if you have two lambda things at state I, you get another one at state I. And if you should have a lambda abstraction thing, so if you had a thing at the shifted state, that should give you a thing back at the original state. Now, this is luckily a restricted inductive family, which means that all the constructors have the form, they tell me an index and I'll tell you exactly something that lands in that index. Here's a little puzzle about non-restricted inductive families. Say I want to define a type on the circle that has a favorite, and it's given by this one constructor that gives me a point in over the base point. Okay? I'm going to draw the picture over here. Sorry for the random board management now as we're getting to the end here. So here's the circle with the base point. And now I want the inductive family that's generated by one thing here. Now what's the size of the fiber of the base point? It would have 1, 2, or infinitely many objects. Someone is smiling, yeah? You all know the answer. You may not know that you know the answer, but you all know the answer because this is exactly the polymorphic version of the identity type as an inductive family. The identity type is some family from given starting point is some family and a type that has one generator at the starting point. So this is another name for the identity type on the circle at the base point. So in general, fat x will be space equals x. So you get the whole helix freely generated in this inductive family. So when you first see it, maybe you're a little surprised, but once you say, okay, that's fine. Okay. That's not the kind of stuff here. I do hope that in cubical type theories we will have support with computation for the restricted inductive families at least, and then maybe one can do sort of on Andrew Swan's trick to do arbitrary inductive families. But for programming with these things, I should say that ACTA is really a good tool. If you actually want to program with this, one thing you want to do is you want to say, well, if I have a decidable equality on the atoms, then I also have decidable equality on these lambda terms, right? And one thing you want to show is that the constructors are injective. And already that, if you do this by hand, just by the recursor, it is really a mess. But luckily, there's now some theory about how it's done in ACTA, so that we know that it makes sense even without K. And
Is there a beta rule or something? Do you put in any equations?
No.
Or is that's it?
That's it. And then I can show that it has decidable equality, so it's a set, and I can also show that it's the same as the right thing. So if you do the usual De Bruijn indexing, the De Bruijn indexing also has this structure, and then this thing will be the co-limit over all De Bruijn indices of the De Bruijn presentation. Okay.
I didn't understand how ACTA helped you with the induction. I didn't understand how ACTA helped you with induction.
Okay. So let me write down one equation. So one wants to say something like the variable constructor is injective, right? One way to say that is to say for every index I, if I have two atoms, A and B, at I, and if variable A is equal to variable B, then A is equal to B, right? Try to write this function just using the eliminator for this inductive family. It's not easy. But in ACTA you can write this. R injective, these are all implicit arguments, I'm going to write them. Say IDP, and then give IDP.
Oh, I see what you mean, yeah.
So
When
this
it uses pattern matching combined with recursion.
combined with you know,
Yeah, not in this case.
very
because
clever
recursion.
very clever way of unifying things.
Yeah.
So what will go on, if I don't think they have the compiler to recursives, but if they did, what would happen is you would have to recognize that this is not the maximally general equation you can write between two variables. I have to generalize this to arbitrary indices. So I have to actually do something for all I and j in I, and then give me I insert a path I equals j, and now of course I change the b to this over j, and then these become dependent paths. This says var I a equals var j p over p. Let's just do the domain. So the domain will be this telescope. But this telescope, by unification, now I have a maximally generic equation, and I can shorten it to all I equals j, all of this thing, a and b, and now just a equals b over p. Okay? So I shorten the domain telescope. I use this injectivity of constructors equivalence to shorten the domain telescope into this. Now I can cancel out the p again to go back to the original telescope, and then it becomes a projection. But it's, I mean, you have to do something. You have to check that this equivalence cannot be any equivalence. It has to be an equivalence that is basically the canonical congruence map in the upwards direction, because this means that this thing will compute correctly when you go back to the original domain telescope. It's a little subtle that it works, but in ACTA it just works.
So that
because
this is, I think, so Connor McBride in the late 90s worked out how to do this with K, so compiling.
Yeah, but Connor did it with K,
and then
and
just
now-
for Coq.
Yes, but Cox has a thesis about how to do it without K using these equivalences.
So it's an extension of Connor's thing that works in hot, which means that rather than having to prove injectivity of constructors yourself from the eliminator, you get it built in.
And also this thing also does that. You don't get this from the this map. You don't get just from the usual injectivity of constructors construction. You have to do this extra step to show that it's fiber-wise over the base to allow you to do this detour. Right. So it's even more tricky than that. Okay. Anyway, let me just finish with some questions. So I'm going to continue to explore this in the GitHub repository. I have some active formalization. Please feel free to explore with me. And so eventually we may want to know what is the correct notion of a nominal homotopy type. And I don't think, I mean, this is not even given the usual nominal sets. But there's also another issue that might come up, which is that in homotopy theory, when you work with things that have a nominal nature, when you swap adjacent variables, it usually costs you a minus sign. So this may well be that in one of the cases where we want an infinity topos, but it's not going to be the one localic infinity topos of the Shanwell. That's going to be a unique infinity topos that's one localic and whose set part is the Shanwell topos. But that may not be the best infinity topos for nominal theory. That remains to be seen what is the correct thing there. Thank you.
Just a quick question and then we'll.
Okay, so yeah, maybe my question is too naive, and maybe you have even said it, but it wasn't on the board, so it was hard for me to figure out. You said lots of stuff about the sigma infinity types,
Yeah.
and then you gave this example, and now I didn't see the sigma infinity back in this example, so I was lost in how this is an example. Of
Yeah,
what
so
you said.
I would like to, you can experiment this with many different settings, but if you want to do the nominal thing with b sigma infinity, you would take I to be b sigma infinity.
Okay.
You would take S to be the shift by one,
Mhm.
and you would take A to be this Adams type, the canonical.
Okay. Okay.
But the same definition also gives you the De Broglie version of natural numbers, where you take I to be net, you take S to be successor, and you take A to be finite, the fin family that gives you a set of n elements.
Other questions?
Okay, thank you.
All right.